All right. Let's use everything that we've learned to go ahead and do our next example. So example 54 on page 7 is at what point of the paraboloid y equals x squared plus y squared is the tangent plane parallel to the plane x plus 2y plus 3z equals 1. All right, so the first thing that I'm going to do is I'm going to look at, okay, in order for these two planes to be parallel, the vector that both of these use for their normal vector has to be parallel. And so what we're going to do is we're going to go ahead and find for this plane, right here, we're going to go ahead and find the normal vectors. So for the plane, our vectors are going to be 1, 2, and 3. Again, those are just going to be the coefficients of our functions. Now, here we have a paraboloid, and what I'm going to do first is I'm going to go ahead and get all my variables on the same side. X squared plus z squared minus y. Alright, now again, that's not a plane, right? That's not a tangent plane. So in order to find the tangent plane, what I'm going to do is I'm going to go ahead and find my gradient of that. And so if this is our function, and again, we'll say that, hey, that's our function f, then we want to find the gradient of f. And when we do so, we're going to find the gradient. We're going to find the partial of x, partial of y, and the partial of z. So now let's go ahead and let's take our function and let's take the derivatives of each. So the derivative with respect to x is going to give us 2x. Derivative with respect to y is going to give us negative 1. And the derivative of z is just going to give us 2z. Now, what this tells us is that at a point on our paraboloid, we don't know what the point is yet, but at a point, our tangent plane is going to have a vector that is comprised of a normal vector that is comprised of 2x, negative 1, and 2z. Now, because we know that that's going to have to be the normal vector for our tangent on our paraboloid, and we want it to be parallel to our plane at x plus 2y plus 3z equals 1, what we're going to have to do is we're going to have to find a point x sub 0, y sub 0, and z sub 0. All right. So I'm going to go ahead and I'm going to substitute in for this vector our point at x sub 0, negative 1, and then 2 z sub 0. For our initial x and initial z. Again, I didn't have to do one for y because y is always going to have that normal line of the component of negative 1. And now, I know that this vector is going to have to equal 1, our other parallel vector times some k, right? Times some scalar, right? It doesn't have to equal exactly, as long as it's, equal to some, that vector times some scalar, it's going to be parallel. So now what I want to do is I want to be able to solve for k. So what I'm going to do is, I can divide this vector by that vector, right? And I could do all of it, but I'm just going to go ahead and do the y's. Why am I going to do the y's? Because on the left side, that negative 1, this negative 1 does not have a y sub 0 component. So I can actually solve for k if I use the y components. So k is just going to be negative 1 over 2. So now I've solved for my k component. And so when I'm looking for my x component, now I can say, okay, I have 2x sub 0, negative 1, 2 z sub 0 is equal to, and now I know that it has to be equal to, now that k is negative 1/2, negative 1/2, negative 1, and negative 3/2. And now I'm going to go ahead and set both of my points equal. So x sub 0, 2x sub 0 is going to be equal to negative 1/2. I'm just going to set the components equal to each other, and 2z sub 0 is going to be equal to negative 3/2. And now I'm going to solve for x sub 0, so divide both sides by 2, we get negative 1/4 for my initial x, and for my initial z divided by 2, we get negative 3/4. All right, now I have my initial x, I have my initial z. Now what I'd like to find is my initial y. How can I find my initial y? By going back to my equation. It's y equals. So I'm going to have y sub 0 is equal to, it was x squared, so negative 1/4 squared, plus z squared, which is negative 3/4 squared. Alright, so we do that. Negative 1/4 squared is going to be 1/16, plus negative 3 squared is going to be 9/16. So 1/16 plus 9/16 is 10/16. Let me write that 10 a little bit better. 10/16, which is going to reduce to 5/8. And so we found our initial y. So the point is going to be negative 1/4, 5/8, and negative 3/4. And that's the question. Yeah, at what point? And that's the point where the tangent plane of our surface is going to be equal to the plane, or is going to be parallel to the plane x plus 2y plus 3z equals 1. Alright, I'm going to continue this just because this last part is basic. It's no work. It's just, talking about the significance of gradient vectors. So on one hand, we know from the gradient vector, we know that the gradient vector gives the direction of fastest increase of f. On the other hand, we know that the gradient vector is orthogonal to the level surface S of f through p. Combining these two properties, it's going to be quite compatible and intuitively because we move away from P on the level surface S. The value of F does not change at all. Therefore, it seems reasonable that if we move in the perpendicular direction, we're going to get the maximum increase. So every time we move in the perpendicular direction of our contour lines, we're going to be going in the maximum direction. In like manner, we consider, a function f of two variables and the point x sub 0, y sub 0 in its domain. Again, the gradient vector gives the direction of fastest increase of f. Also, consideration similar to our discussion of tangent planes, it can be shown that the gradient of f is perpendicular to the level curve f of xy equals k that passes through P. Again, it's intuitively plausible because the values of f remain constant as we move along the curve. So if we consider a topographical map of a hill and let f of xy represent the height above sea level at a point with coordinates xy, then a curve of steepest ascent can be drawn by making it perpendicular to all of the contour lines. So again, it's just if we're starting at a certain point. So if we start at this point and we go perpendicular, going perpendicular along this line is going to lead us to the curve of steepest ascent. Same thing if, we're starting here. I like starting here because it's a little bit easier. All right, perpendicular to this point is going to be there. All right, perpendicular again. Whoa. It's going to be there. Perpendicular there. And again, we're just going perpendicular in both directions and they have to meet each other. And I'm not going to, because it's going to be too small. Again, all right. A line perpendicular. Let me zoom in. Yeah, all right. And a line perpendicular are going to be the steepest ascent. The line perpendicular there and a line perpendicular there. It's going to be the steepest ascent, and so on. All right, and that's what, this last part is just telling us how we can go along doing steepest ascent. All right, that's it for the notes. Hopefully that you've enjoyed that. Again, it's a long, because there's 8 pages today. But that's it. Friday, you technically have off if you haven't finished your tests already. You have that day to work on it. And